So we now go to the next part, is to try and explain how the motor effect actually comes about. Why is this effect happening? Now, remembering, let's just say what the motor effect is. The motor effect is a current carrying conductor. That is a wire carrying a current. In other words, electrons are moving in this wire. When it is in the presence of a magnetic field, experiences a force, a push or a pull. And we now need to explain that. So here we are. We have a current carrying conductor. Let's put a current in it. Now I'm going to make the current go down. Okay. So what we're going to do here is, if the current is going down, then what will be flowing up is electrons. The electrons flow in the opposite direction. So let's put some electrons here, and they're going to flow upward. You find this diagram in your book. Okay? Can you all see it? So it's on page 2. Now I'm going to explain it, and I'm going to give you enough time to take what I've said and write it in the column beside this to try and explain it. So firstly, rather than take notes as you go, understand what is going to happen. Okay. Now these are all electrons here. Okay. And we know from our first introduction to this topic that a charged particle, when it moves in the presence of a magnetic field, moves in a circular motion. Because that's what they do. Charged particles move in a circular path when they come into the presence of a magnetic field. So if the electrons are moving in that direction there, remembering the current would be moving this direction. So electron flow is opposite to current. The B field, this is the magnetic field going across here, is going left to right. Now, using our three-fingered rule, the FBI rule, force, magnetic field and current push rule, let's have a look at what happens here. So we get your index finger, which is the one that is allocated to the B, make it go in that direction, which is right to left. Okay? Now the current, because the electrons are flowing up, your thumb, which is the current, will be down. Extending the force finger, we will be pushing each of these electrons into the board. Okay? So all of these electrons will no longer go straight up in that direction. They'll go up and slam into the back of the wire. Are we okay with that? They get slammed into the wire. Now, as they get slammed into the wire, these electrons, technically they can't do this, but we'll just assume they can for euros, all the electrons will slam into the side of the wire, pushing the wire into the board. Are we okay with that? So each of the electrons goes into the board, pushing things. Happy? Now, the one over here, it's hard to visualise that. So what we're going to do is we're going to redraw this so that we see it from end on. And the second diagram is putting in some dots with blue. Oops, that was a line. Right, what do these dots represent? Magnetic field coming out of the board. Okay, so we'll get the electrons to go in the same direction again. Remember, these are just a cylinder, so them moving up over here is the same as them moving up over here. Okay, so this time I'm looking at this over here, but we're looking from this vantage point here with my eyelashes. Okay, so are we okay that we're looking end on? So this diagram in this position over here is looking like that. Now, once again, which direction would current be? If electrons are flowing up the wire, then current must be flowing down. Current is always in the opposite direction. So using our three-fingered rule, this time point out of the board, the current is down. What happens to each of these electrons? They get pushed to
that way.
that way. What's that way?
To the left.
To the left. Good.
Okay.
Okay. So in that case, all of the electrons, all of the electrons get pushed into a circular motion into that direction. Now, if they are pushed into a circular motion, have they got much room to move in a circle? No. So what will happen is that they will start imparting their momentum to the side of the wire. So we impart, this is the expression we use, we impart momentum into the wire. So as the electrons are made to move in a circle, the circular motion, the circular path is unable to be completed to make them into a full circle. So as they move sideways, they impart motion into the wire, and as a result, the wire moves in that direction. Okay, with a force. Are we okay with that one? Okay, so in your book on page 2, there's these two diagrams, one under another. So you need to take a few moments to explain, take the time to describe what you see in front of it. So you need to do the following. So you would say in the diagram, you refer to the diagram, the electrons are seen to move up the wire. In that case, current must be moving down the wire. Using your right-hand push rule, that's the name of it, okay, the right-hand push rule, we see that using this configuration, the electrons will be pushed in a circular path towards the back of the wire. Now, looking at a different orientation so we can see it much more clearly, we would see the same situation, but now we can actually do and draw the curved paths as they go into the side of the wire. When they go into the side of the wire, we use the expression, the electrons impart or transfer is another way we could say that, if you prefer to use the word transfer momentum into the wire, and we are pushed in one direction. Okay, take a few moments and write that up, please. We now move to looking at the motion of the wire. Second explanation. They're equally valid explanations, but when you come to the HSC, you have to explain it. You choose the one that you feel more comfortable with explaining. That one there was explaining in terms of the motion of the electrons. And you could be asked to explain the motion of the wire in terms of the momentum of the electrons. Or you could be asked to explain it in terms of the magnetic fields surrounding the wire and the presence that it's in. So let's have a look at the second way of explaining this. Now, on this diagram up here, we have, just to zoom in, there's my zoom. We have a diagram that shows the magnetic field around a current carrying conductor. And from year 11, we know that all wires have a magnetic field surrounding them. And to work out the direction of the magnetic field, we use the right-hand grip rule. Okay? So if the current is flowing in this direction, the current is flowing in this direction, then we place our thumb, that's a thumb, now, in that direction, and the fingers loop in the direction of, there's my fingers, of the magnetic field. And we know that the path is circular. They form a circular magnetic field around it. So if the current is going up, as in this diagram here, we see that the direction of the magnetic field is a circular form going in that direction around it. Okay? So here, this is you don't see it very well in the diagram, but if this is a dot in that position there, that means that the current is coming out of the page. So placing your thumb pointing out of the page, and releasing our fingers, the curl of our fingers says that the magnetic field is in this direction here. Okay? This here on this second diagram here is an X, that's an X going to the page there. That means it goes into the board. If it's going into the board, pointing our thumb in, as everyone's doing, and releasing your fingers, you see that the magnetic field flows in the opposite direction. And this is called the right-hand grip rule. Okay. So we did that one last year. At the moment, the right-hand push rule is used to find the motor effect. The right-hand grip rule works out the direction of a magnetic field around a wire. Okay, so now we know or have remembered how to, whoops, let's go back. Let's go clear my annotations. Zooming down. Okay. We're now going to have a look at putting a wire. Now the wire is going to be placed in the centre here, and this is it looking end on. So this is a wire coming out of the page. Remember, a wire is just basically a very long thin cylinder. So that's the top of the cylinder. And we want the wire to have current going out of the page. So I'm going to put a dot in the centre of that. Okay. Now, using our right-hand grip rule, we realise that it's this idea over here. This is the one which has the dot coming out of the page, and the magnetic field around it is in the anti-clockwise direction. So in pink, I'm going to draw around it the magnetic field. 3 will be enough. And we're going to put arrows. I'm going to put quite a significant number of arrows so we can see the direction all the way around. We really only need 1 arrow, but I'm just putting it so that we've got a significant number. Okay. Now, in a few more moments, I'm going to use the word flux. Now, flux is just a Latin word meaning flow. And when two things flow in the same direction, we get smooth flow. When two, say, streams flow in opposite direction, we get turbulent flow. So here at the bottom, we're going to notice that the pink magnetic field from the wire is flowing that direction, and so is the magnetic field from the external magnetic field flowing in the same direction. So these are flowing together. We get a nice smooth flow. So all of these, we get smooth flow down here. So let's write the word smooth flow. And flux is what we say there. So smooth, nice, gentle, nothing turbulent. But notice what happens up the top. Up the top, I'll use orange for this, we have B going this direction. The magnetic field going this direction. Okay. But which way is the main magnetic field going? The opposite direction. So remember, it's still going, what colour? It's still going this direction. So here we get turbulent flux. Turbulent flux. Okay? Now, what does it look like when the two fluxes combine? And here we are, here's one I prepared earlier. Okay? What happens is, down here you can see where the two smooth fluxes are flowing nicely together. You can see down here we get nice smoothness. Okay, so yellow is smoothness. Up the top, here, we get turbulence. Okay, where the the direction of the flow is trying to trying to bend around each other. What are all of these? These, remember, this is a field line. So is this a field line? We know from year 11 that one thing field lines can do is they must not touch and they must not cross. So if you've got field lines that flow together, this is easy. They just they squeeze past each other. But when some field lines flow in one direction like that, and the other field lines flow in a direction like that, then what happens is that this field line has to go in, around and outside it because they cannot cross. This causes turbulence. If this was an airplane, this wing would rise. Okay, and that's why airplanes rise, because you can't have two different types of flux. We have one flow going one way and the other flow going the other way. Same thing here. What way will this wire be pushed to try and even out the flux? Up. So we notice that the wire starts to get pushed out of the magnetic field to try and untangle this turbulent flow, to make this a smoother area. And we often say that the wire is pushed from high flow, this is high flux, to low flux. So the wire is pushed, let's write that down, from high flux. Now high flux is a nice, smooth, tight flow, okay, to low flux. Low flux meaning low flow. Up here, can you notice that there are no flow lines up here. So there's not many lines going up here. By the way, that line there is not a field line, it's just the force line, the direction of the force. Okay, so it's not a field line. Okay, so in a few more moments I'll give you time to do that as well.
Why is that top section turbulent flux in?
Because the main magnetic field is going that direction, but the magnetic field from the wire is in the opposite direction. So the two magnetic fields oppose each other. They've been pushed into each other, and they are not allowed to cross or touch.
Yeah.
So one has to flow around the other. Okay?
But doesn't that mean like the whole diagram there, that's called a turbulent flux?
No, this section here is turbulent.
Just that section?
Just that little bit, the top bit there. See how all the lines are bending around each other?
Yeah.
That's called turbulent flux.
Oh, okay.
Here, down here, the lines are smooth and they're flowing together and they're tight together. Okay? So that's a smoother flux. But when I'm saying we don't normally use the word smooth flux or turbulent flux, we use the words high flux for when they flow together, the lines are tight together, and low flux where there is lots of gap.
So the wire itself has two types of flux.
No, it's only got the pink line around it.
Yeah.
Okay, the pink magnetic field is from the wire.
Yeah.
Because it's in the magnetic field that we're putting in from another magnet or so, then some of the magnetic field flows in the same direction, some doesn't. Okay? And this wire gets pushed from its position here out because it goes from high or smooth tight flux into the turbulent flux. Okay? It's the same as what we do with wings on a plane. On a plane, by using a shape like this, or airfoil, we create high flow underneath, very fast air moving underneath, high flux, and turbulent flux on top of the wing, and the wing is pushed up. Okay? Rightio, take a few moments to see if you can try that. Right, we move now to the next page of your notebook, where you see this. The motor effect is given, and I've already told you the formula for the motor effect is F equals BIL sine theta, or F equals Bill sine theta, because I had to remember it. You have it on your formula sheet that is given to you. Now, because of this formula, you have 4 different proportionalities, because they are simply if F equals this thing over here, then F must be proportional to every member on the other side. So having a look, that means that F must be proportional to B, F is proportional to I, F is proportional to L. Now, you're required, and you're going to do this tonight, you are going to be required to explain why doing one thing will increase the force. So if I increase B, what is B again? It's the magnetic field. So if I increase B, I will also increase the force. Why? Why does that happen? Why is increasing the magnetic field strength? In other words, here is my wire, and here is a magnetic field going through it, and I've got a current going down the wire. Why does making B stronger, putting more B on, why does it make the force get bigger? Good, exactly. Remember, the first explanation of the motor effect is electrons moving in the wire. If you increase B, you increase the force that those electrons impart their momentum to the wire. So if increasing B increases the force into which they smash into the side of the wire, if you want to put it that way. Okay? So by increasing B, you increase the force on each of the electrons. Increasing the force on the electrons makes them accelerate faster, and when they accelerate faster or move faster, and then they collide with the side of the wire, they impart more momentum into the wire, and that momentum is called impulse, and that's the movement, the force, the push. Okay? Are we okay with that one? Why does increasing current do the same thing? Why would if I increase the current, I increase my force? Well, what is current? Current is the number of electrons moving down the wire. So if you have only 3 electrons over here at the moment moving down the wire with a certain current, but if I double the current, I now have 6 electrons moving down the wire. Does that make sense? If I've got more electrons moving down the wire and I put them into a magnetic field, that's more electrons imparting their momentum into the side of the wire. More electrons, more push. Are we okay with that one? What about increasing the length? Well, let's just rub out half of my wire here. Without the magnetic field actually existing, are there already electrons in the wire? Yes. Here, I've got a diagram which has only 2 electrons in the wire because it's a short thing. Now, well, obviously there's more than 2 electrons in a wire, isn't it? It's billions of them. But for diagrammatic purposes, 2 is enough. If I increase the length, I have more possible electrons that can be in the presence of the magnetic field. More electrons, more force is imparted into the side of the wire when the magnetic field is turned on. Okay. So these 3 are quite easily described. The last one is the angle. Now, it's not just theta, it's sine theta. So to understand this, let's just put a magnetic field going down here for a few seconds. And a bit more. And here is my wire.
What's the angle? Like the angle of what?
I'm just about to tell you. That's I'm about to talk about the magnetic field and the angle. Okay. Now, notice at this moment, I have B going directly down the page, and I've got the current. Let's make it go in this direction over here. The wire makes an angle of 90 degrees with the wire. Okay? Now that means the electrons are all moving in this direction. Okay, so we'll put it here. Let's do our push rule to work out which way this wire will be pushed into or out of the board. So remember, the current is going this direction, current is going that way, B is going down, so the right hand push rule, so let's do that, that. Which direction is it?
Going into the
Into the board. Okay, right here. Now, put your 3 fingers up in the push rule. Good, okay. That's what your 3 fingers are supposed to do. Now, let's start twisting the wire and put it in. So rather than being at 90 degrees now, I'm going to make the wire go up like this. Okay. And let's now make that 30 degrees. Okay. What do you notice about 2 of your fingers? 2 of your fingers are starting to come towards together in like a scissor motion, aren't they? They're supposed to be at right angles to each other. So is the force going to be as big? No. The actual answer is, having a look at this, putting your hands down, okay. If I twist the wire into that orientation, the electrons are effectively only moving this amount from there to there. Okay? They're only moving that direction sideways in the field. They're also moving this direction vertically in the field. We're going to get there in a few more moments, those things. So what's the effective sideways length that we are moving? So making a triangle, if that's the length of the wire, this is a right angle here, this would be 30 degrees. What's this length down here? It's L sine 30, isn't it? Just by trigonometry. Okay. Now, getting your 3 fingers again and pretending that the current is going this direction, that part there would be the same. Current is going this direction, B is going downward, F would be inside the page. Are we okay with that? So F is going in. Now let's look at this other vertical line here. Let's see what would happen to any electrons which actually travel vertically in the field. So if the electrons are flowing up, then current will be flowing down in that direction. So what current is now travelling in the same direction as B, isn't it? That means that 2 of your fingers of your push rule are now travelling in the same direction. Can you make 3 right angle fingers where 2 fingers are collapsed onto each other? No. So what would be the force on those vertically? 0. Okay? So there is only this effective motion across here. So in other words, what I'm trying to say is the last thing here is not just simply sine theta by itself. It's actually L sine theta. Whoops, it's wrong colour. It's L sine theta. That sine theta at the end is shrinking the effective length that is moving at right angles to the field. Only when you move at right angles to the field do you get a force on you. If you're moving it with the field, you get no force on you. So let's just write that down. Electrons moving with the field. And we might just write current moving with the field have no force. Okay. This gives us an idea or an understanding then that we must be able to come up with a formula that works. So we have maximum force if we are at 90 degrees. So I'm just going to take that off. Yeah? Max force theta equals 90. No force theta equals 0. Let's see if the sine angle is working. What is sine 90? It's 1. So in the formula F equals BIL, sine theta, if we have a wire which is at 90 degrees here, perfectly perpendicular, is there any reduction in our force? No. What is sine 0? In other words, you now have the wire vertical in the field. Sine 0 is 0. So does this addition of sine theta make the effective force reduced to 0 if we twist it all the way around? Yes. So what is theta? Theta is the orientation to the field. And it reduces, I might just take the next slide here. So theta is the orientation of the wire to the field and reduces the effective length L in the field. So, where do we measure the angle from?
So,
Yeah?
what if the angle is like smaller than 90?
Yeah, just perfect. Great question, which is what I was about to ask. Okay, so if our field is going down here and the wire is moving, is this direction here, there is the wire, then the angle is this one here. But what happens if I use, that's the acute angle, what happens if I use accidentally the obtuse angle? Well, what do we know mathematically? If I use sine 30, it equals a half, because acute angle 30 is a half. But the obtuse, which is 150, is also a half. So it does not matter if you take the acute or the obtuse angle. But it's got to be the angle between the wire and the field. Are we okay with that? So, yeah, question about if you keep on twisting it, and then it becomes more than 90, means it becomes obtuse, which is the same as the acute. So it doesn't matter, because sine is a great, easy trigonometry ratio. Okay, can we have a look at in the last few minutes? Got that? I've given you, there's a worksheet 1A. And we're going to do question 1 together, and then you'll do the rest of the sheet for homework. So getting up 1A. Oops, it's a recent. Okay, let's do it together here. Now, when working with these, we're going to be using all the time, we're going to be using the formula which is F equals BIL sine theta. So there's our motor effect formula. Okay, you need to always find a value, and after you find the value, you need to work out if it's a direction in or out of the page. So here we are going to find the force and the direction using all of this information. So just enlarging this for you so you can see it a bit better. Let's get our formula up. Where are we? So we have F equals BIL sine theta. Well, the length is 10 centimetres. What do we know about centimetres in these formulas? We can't use them, isn't it? So it's 0.1 metres. Here is the current, it's 2 amps. Here over here is the strength of the magnetic field. The strength of the magnetic field is 3 Tesla. And Tesla, as used to remind you, is like amperes is for current. Tesla is the unit of strength of a magnetic field. So all we need to do is the angle. To do the angle, you need to draw the field between the two. And we know that at the ends of these bar magnets, the magnetic field would go from north to south. The current is going directly up in that direction there. So what's the angle? Theta is 90 degrees, isn't it? So popping in all of those numbers, we get B as 3, I is 2, the length is 0.1 times sine 90. We know that sine 90 equals 1, so we can leave it out of our calculation. And 3 times 2 times 0.1 is 0.6 newtons. Now remember, it says find the force and the direction. You should always find the direction anyway because a force is a vector and it always requires a direction. So using a 3-finger push rule, using my diagram that I've put more stuff on, B is going this direction, I is going up. So using those there, thumb going up, B this direction.
My apologies for this interruption, staff and students, but I've got a very important message. You've got to just have the attention of all classes, please.
And so it's out, is it, we say out of the page?
We actually write that out.
You're out of page, yeah. Out of page. Right, the next one there, I find it always good to redraw the thing. Looking side on, if that's the north and that's the south, the current is going into the board. So the current will be going, sorry, no, it's coming out of the board, so it's a dot. The force is going up the page there, and B flows from north to south, so B is going this direction. Okay? So let's work out, we've got to find the magnitude and direction of the current. Okay? Well, we know the direction of the current out of the page, isn't it? Well, let's see if it's right. So we know the force is 8, B is 12.5, times I is what we're trying to find. Length is 25 centimetres, so it's 0.25. And what's the angle between the force and the current force and the magnetic field? They are all at right angles, so it's sine 90. Rearranging that, could you get a value for I? .56, do we agree? 2.56 amps. Now we need to work out the direction using our 3-finger rule. B is going this direction, F is going up. We need to find I. So using that, point that direction, F up, current must be coming out. So we confirm the current is coming out of the board. Okay. The last one I want you to do now, before we just go out of here, is I want you to do C for yourself tonight, but I want you to have a look at D. Just very quickly now, what do you notice is the direction of the current and the direction of the magnetic field? They're the same. So when current flows in the same direction as magnetic field, what must be the force?
0.
0. So magnitude and direction of the force is 0. If you have no force, you cannot have any direction, so you can write 0 straight there. This one down here is to do with the solenoids. You have to work out which is the north and which is the south pole using your right-hand grip rule. Try that tonight, as well as question 2, 3, and 4. Question 2, 3, and 4. So all 1, 2, 3, and 4.